Bismillahirrahmanirrahim. Welcome to the Electrical Engineering channel. In this lecture, you will learn how we can transform cylindrical coordinates to spherical coordinates directly. In previous lectures, we saw the transformation of cylindrical components to Cartesian components and Cartesian components to cylindrical components. Similarly, we also discussed the transformation of spherical components to the Cartesian components and vice versa. But so far, we haven't discussed the direct transformation of a cylindrical and spherical coordinate system. So in cylindrical coordinate system, we have three components, rho, phi, and z. In spherical coordinate system, we have three components, r, theta, and phi. And we know that r is equal to x square plus y square plus z square square root. And we also know that x square plus y square is equal to rho square. So we can write r is equal to rho square plus z square square root. So this is one expression, and it is giving transformation from cylindrical variables to r. So r is the spherical variable. Similarly, we know that theta is equal to cosine inverse z over r, and r is equal to rho square plus z square. So cosine inverse z over square root rho square plus z square. This is the expression for theta in terms of cylindrical variables. And finally, phi is equal to phi because phi variable is present in both cylindrical and spherical components. And now we can also transform spherical variables to cylindrical variables. And from this figure, you know that this is the point P and this is the direction vector or unit vector of AR, and this is the magnitude of R distance from origin to this point. This is rho, the distance from z axis to the point, and this is a rho and this is a theta. So from here we can transform r into two components, r cos theta. So this component is r cos theta and this component is r sin theta. So from here rho is equal to r sin theta. So this is one transformation. Similarly z is equal to r cos theta. This is second transformation, and phi is equal to phi. So this is the transformation of spherical variables to rho. This is z in terms of spherical variables, and this is phi, and phi is equal to phi. Now we will evaluate the dot products of unit vectors among the two coordinate systems. So a rho dot ar is the first dot product, and a rho dot ar will be equal to the magnitude of a rho multiplied by magnitude of ar multiplied by cos of angle between them. So from here, you know that this is a rho, so this is a rho, and this is ar, and the angle between them can be evaluated by looking at this triangle. So the angle between AR and A rho is actually this angle, and this angle is equal to this angle, right? And this angle can be evaluated by considering that the sum of all the angles in a triangle is equal to 180 degrees. So this is 90 degrees and this is theta, and this is the unknown angle, and this unknown angle will be equal to 180 minus 90 minus theta. So this unknown angle will be equal to 90 minus theta. So a rho dot ar is equal to cos 90 minus theta, and it will be equal to sin theta, and a phi dot ar will be equal to 0 because phi and r are the two components of a spherical coordinate system, so they are perpendicular to each other, right? So here you can see all three components of the same coordinate system are always perpendicular to each other, so the angle between them will be 90 degrees. Similarly, rho phi and z are also perpendicular to each other, and a phi dot ar is equal to 0. Similarly, a dot ar is equal to cos theta because this is ar, this is az, and the angle between them is theta. Secondly, we will check a rho dot a phi, right? So rho and phi are perpendicular to each other because they are the components of the same coordinate system. So a rho dot a phi is equal to 0, a phi dot a phi is equal to 1, and az dot a phi is also equal to 0. Finally, a rho dot a theta is equal to cos theta because this is a rho, this is a theta. Now the angle between z and r is theta, and rho is perpendicular to z and theta is perpendicular to r. So the angle between a rho and a theta will also be equal to theta. So a rho dot a theta is equal to cos theta, and a phi dot a theta is equal to 0, and az dot a theta is equal to cos 90 plus theta because this is az, this is a theta. So this angle is theta and this angle is equal to 90 degrees. And actually this was a theta, but we have redrawn a theta over here, and from here we can estimate the angle between AZ and a theta, and it is equal to 90 plus theta. So AZ dot a theta will be equal to minus sine theta. So we can write all these dot products in the matrix form. So this is AR, A theta, and A phi. This is A rho, A phi, and AZ, and all the values of the dot products among different unit vectors is written over here. So that is all about our first chapter from the engineering electromagnetics textbook. I recommend all of you students to solve these four problems related to the spherical coordinate system. So if you are able to solve these problems, it means that you have learned all the concepts in spherical components, their transformation, and their values in a convincing manner. So that is all about our today's lecture. For watching more lectures, please subscribe to this channel. Until the next lecture, it's goodbye.